Okay. So we know exponential functions are one-to-one. We talked about how if we drew a horizontal line through the graphs of exponential functions, they would only cross our function at one point. And so we know they are going to be invertible. And obviously they are invertible because logarithms are their inverses. So normally when we talk about the inverse function, we use this little notation here, f inverse, which looks like f to the negative 1 power. We actually don't use that notation when we're talking about logarithmic functions because we actually use this notation of log of x with base a as the notation for logarithm. So we don't actually have to use that f inverse notation in this case. The way you read a log is you have log of x, which is of course the value at which we're evaluating the log. So log of x with base a. Okay, and of course, since they are inverses of exponential functions, let's say we have our basic exponential function here, 2 raised to the power of x. So if I'm evaluating this function at 3, that means I'm replacing my x with the number 3. So that's 2 times 2, which is 4. 4 times 2 is 8. So 2 multiplied into itself 3 times will give us 8. Now when we're writing this as in the inverse notation, we would basically say if I'm taking a log on the number 8 with the same base 2, my answer should come out to be 3. So the idea is the base of your exponential function, which is base 2, will be the same base on your logarithmic function. So if this guy is base 2, my logarithm is also base 2. Now a logarithm is always going to give you the exponent. So you can see here we're saying in general, log of x with base a is the exponent that is used on the base a to obtain the value of x. So the idea is when we set up this logarithm, you're asking yourself the question, 2 raised to what power will give me 8? And that answer is going to be 3. So a logarithm is always going to give you the exponent. As they're telling you here, the log is the exponent for that base. So this is something you will definitely need to remember, is how to go back and forth from the log notation to the exponential notation, or from exponential to the logarithmic notation. So remember what I said. The same base that we have for the logarithm is going to be the same base for the exponent, or vice versa. A log always gives you the exponent. So this y will become the exponent on your base a when we write it as exponential. And this x that the log is being calculated on is going to be the answer for our exponential notation. So base a here, the exponent y will obviously go as an exponent here, and then that will be equal to x. So this is something you will definitely need to get comfortable with, going back and forth between the logarithmic and exponential notation. Okay, so let's go ahead and see how we can solve logarithmic equations like these one here. So they are giving us log of 1/16 with base 4 equals y, and of course we're trying to find what that answer for y will be. So let's take a look. So how do we find that y? So this is actually where we're going to convert this into an exponential form and then simplify it. So remember again, my base 4 here will become the base 4 for my exponential function. A logarithm always gives me the exponent, so that y becomes our exponent on 4. And this will equal what we have in the parentheses, 1/16. So this is going from the logarithmic form into the exponential form. Now, back in section 4.1, we had talked about the one-to-one property of exponential functions. And just to remind you what that property was, we said as long as our bases are the same, we can say x1 is equal to x2. So the idea is if I can get both my bases to be the same value, then using the one-to-one property, we can say our two exponents are equal to each other. So that's what we're actually trying to do here. Once we convert this into the exponential notation, we need to try and get the same base on both sides. So how can I write the number 16 as base 4 to some exponent? Yeah, 4 to the negative 2, but let's break it down into steps. So the first thing we'll do is just rewrite 16 as 4 to the second power, because 4 times 4 will give us 16, right? Now it's still in the denominator because I've got 1 over 16 or 1 over 4 squared. So I need to take it from the denominator to the numerator level. Since it is positive in the denominator, when I move my expression, my exponent will become negative. So that's where we get 4 to the negative 2 from. And we have 4 to the y on the left-hand side. So this is where our one-to-one property for exponents is kicking in. Now that both my bases are the same, we can say by the one-to-one property, y equals negative 2. So here what we're actually doing is taking a logarithmic expression and converting it back into an exponential form so that we can solve it and get our value for y. Questions on this guy? Number 1?
I still have no idea how to put this in a calculator.
Yeah, if you have a scientific calculator, well, the newer ones kind of let you fudge it a little bit, which I don't like. But at this point, we won't be able to use calculators to solve this. We have to wait till 4.3 before we can do that. Because the only two bases on your calculator is going to be the log and the natural log keys, and these bases cannot be solved with those. Okay? All right, let's see how to break down number 2 here. So 2 is given to us as log of 64 with base 2 equals y. So same thing, we're trying to find y in this case. So let's go ahead and take a look at him. So log of 64 with base 2. Again, convert this into exponential form first. So since my base is 2, this will become 2 raised to the power of y equals 64. Two raised to what power will give us 64?
6.
6? Okay. 1, 2, 3, 4, 5, 6, right? So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64. Alrighty, very good. So it's going to be 2 to the 6th power. Same thing, now that we have our matching bases on both sides, we can say by that one-to-one property again. Y equals 6. All right, guys, let me see what you can do for number 3. So log of 125 with base 1/5 equals y. So convert it into exponential form first, and then times e by using the one-to-one property, how to get y equals. Jose, do you have an answer?
I think so.
What do you get?
The y equals -5.
-5. No.
No, I don't know.
I think you're almost on the right track. If you just do your calculation again, I think you should be able to figure out where you went wrong. It's a very simple mistake, actually. Okay, so let's start by rewriting it as the exponential form. What did you get? No? Okay, we'll ask him again. What will this look like in the exponential form? Yeah. Very good. So you will have 1/5 raised to the power of y equals 125. Very good. Right, so again, the same base for the log will become the base for the exponential function. Raised to the power of y equals 125. Now, since you have 1/5 y, what should we do? Take it back to the numerator level, right? Because it's in the denominator level. We want both our bases to be on the same level. So you can actually take that 5 to the numerator level. And obviously, since there's no exponent on 5, you can think of that exponent being 1. So when we take it to the numerator level, that will just become 5 to the -1. Multiply the 2, you get 5 to the -1. And remember in 4.1, we had actually looked at a graphing example, which was 9 to the -x or 5 to the -x or something like that. It's kind of the same idea. When you have a fraction as your base, when you take it to the numerator level, you'll end up getting a negative exponent. Now, on the other side, 125 needs to be rewritten as 5 to some exponent. What should that be? Yeah, it's 5 to the 3rd power. That gives us 125. So again, 5 multiplied into itself 3 times. 5 times 5 is 25. 25 times 5 is 125. So it's 5 to the 3rd power. And then once we get our bases to match, you're just setting your y equal to that number, or in this case, we are going to have -y equals 3. Move that negative to the other side. Your negatives will cancel out, giving you y equals -3. So here's something you should notice. In that first example, I had base 4 and it, bless you, was equal to 1/16, right? 1 on the numerator side, 1 was on the denominator side. When we have this fraction involved, oh, come on, we ended up getting a negative value for y, right? When they were both on the same side, we didn't have to move anything. It ended up giving us a positive value for y. Here again, my base was a fraction, but this number was not a fraction, right? So when I have that difference, I again ended up getting a negative value for my y. So anytime you get one of the sides being a fraction, you're going to end up getting a negative value. Okay, questions on these first 3 examples? Alrighty, let's take a look at our next thing here. So talking in terms of domain and range. Now remember, for an exponential function, we had a domain going from negative to positive infinity. We said all real numbers could be used, but as far as the range went, it only went from 0 to positive infinity, not including 0 because we had that horizontal asymptote on the x-axis. So since exponential functions and logarithmic functions are inverses of each other, that means your domain and range will also invert, right? When we're looking at the logarithmic function. So the range of 0 to infinity, not including 0, will actually now become the domain of our log function. And the domain of negative to positive infinity will now become the range for our log function. So those domain and range will switch places for the log function. You will not be able to find a logarithm for negative numbers or log for a 0. And even though they are talking about log base 2 and log base 3 here, on your calculators, use the log or the natural log key and see what happens if you did just log of negative 4. What does your calculator say? Log of negative 4.
Error.
Error? What kind of error? Does it say domain error?
Domain
Not yours? Well, I guess he's not fancy enough.
error. You remember what the problem on Monday last week?
Yes, I do. Yeah. So some calculators will say error, some will say domain error. It just depends on your calculator, what I guess is programmed in there. Okay, if you tried log of negative 4, now try natural log of 0. Do you have the ln?
Yes.
Yeah, so ln 0, or you may have to do 0 ln.
Error.
Error again, right? And you can try this with both log and natural log. You're going to get errors for both of them. That's because, remember what we just talked about, your domain for a logarithm function is starting at 0, but not including 0, right? Which means it can start at 0.00001, and it will be fine. But if you try to use 0 itself, or anything that is less than 0, which are these two numbers here, you're going to end up getting an error because it's not part of our domain. So that's why you're going to get a domain error. With one exception, when we use our x value as 1, so if you try to do log of 1 or natural log of 1, for both of those, you should get 0 as the answer. And that's actually coming from the idea of when I rewrite my base a raised to the 0 exponent equals 1, you're looking at this guy right here, right? Anything raised to a 0 exponent is always going to end up giving you 1. So it really wouldn't matter what base we had here on the logarithm. If you're doing this at the value of 1, you're always going to end up getting 0 because that's coming from the 0 exponent. Okay? So no negatives in our logarithm, no zeros in our logarithm, and every time we use a 1, we're going to end up getting 0 as our answer. Okay, so this is where those log and natural log keys on your calculator come from, because those are, in fact, the two most common logarithms we use. So if you have a base 10 logarithm, so right here you can see it says the notation of log with the base 10, we actually don't need to write that base. So if you see something that just says log of x or log of some number, it's understood you're looking at the base 10 logarithm. So you don't have to explicitly write that 10 on your base. In that same way, when we are looking at a base e logarithm, that's your natural number e. So again, instead of writing it as a log with base e, we just write it as ln for natural log. So the base 10 logarithm is what we call as a common log, and base e logarithm is what we call as the natural log. And those are the two keys that you will normally find in your calculators. Now, you know, of course, calculators are getting fancier. So some of them will let you type in a different base, like a base 2 or base 3. But again, it just depends on the model of your calculator. So some of them will let you type those in, some will not. So for the ones that do not, we'll need to use the base change formula. Okay? Base change formula is where we'll be able to change our base from anything. So it's a base 2, you can make it into a base 10. If it's a base 5, you can make it into a base E, or you can change it to a base 4, anything. But that's what we'll actually need to use to manipulate our calculators to solve those for us, okay? And that's in next section. So let's get into some definitions here. When we're talking about the common log, that's your log with base 10. Remember, again, we don't need to explicitly write that base 10. So when you convert this into the exponential form, that's going to be 10 raised to the power of y equals x. When we're talking about the natural log, again, that's ln, but we know that's base e, so this will become e to the power of y equals x, and you can see those are mentioned right here, okay? So using that idea, they're asking us to solve these next couple of examples. So let's start with number 4. So we are given log of 10 to the 6th equals y. So please remember, when no base is mentioned, that means it's base 10. So that's our assumed base 10. So when we convert this back into exponential form, it's going to be this base 10 raised to the power of y equals 10 to the 6th. Yeah, y equals 6. So again, by that same 1-to-1 property for exponential functions, we get y equals 6. Questions on this guy? Okay. We've got example 5, which is talking about log of 0.1 equals y. So what will this be in exponential format?
10 to the y equals 0.
Yeah, so again, that 10, which is not mentioned here, 10 to the y equals 0.1. Now, how can we write 0.1 as 10 raised to some exponent? Oh, think about it a little bit.
Oh, 10 to the negative
10 to the negative 1. So this is where it's coming from. 0.1 is the same thing as 1/10, right? Because your 1 is in the 10th place, so that means you're dividing by 10. So 1 over 10, move this back into the numerator. So that exponent of that 1 will now end up becoming 10 to the negative 1. So rewriting this guy. Oh, I didn't mean to do that. Go away. Will be 10 to the negative 1, so y is negative 1. There you go. Okay, let me see what you guys get for 6 and 7. 6 and 7. Got an answer? Okay, hold on 1 second. Okay, just show me fingers what the answer is. Okay, good. So natural log has what base? E. So what will this guy be in exponential form?
E to the y equals e.
Okay, so let me get my little color. So this is a base E, right? So we write this as E to the y equals that E in parentheses, right? Now what's the exponent on that E in the parentheses? 1. So again, since my bases are the same, okay. Dazzle me people with number 7. What's our y? Yeah, very nice. Did you guys hear what he said? Maybe negative 5. So this is natural log of e to the negative 5 equals equals y. So again, that e base, which is not mentioned here, will be e to the y equals this answer in the parentheses, e to the negative 5, right? Again, both our bases are the same. So y equals negative 5. Okay, before we move on to number 8, I want to point out two things to you, or actually the same thing twice, because in 4.3 we'll talk about it. Right here in the first example, you can see how this was base 10 and this is also base 10. So technically there's a rule that says when both our bases are going to be the same, your answer is always going to be that exponent that you have. So as long as these two bases are going to match, we will always get 6 or whatever that exponent is as our answer. And this is the same thing that happened right here in number 7. Come on, buddy. So this was also a base e. This is base e. So since both these bases match, our answer came out to be that exponent, negative 5 again. Does that make sense? Yeah? All right. What's happening on number 8? Yes.
But why does the negative 5 work on that one, not the other?
Which one do you mean? The one before that?
Yeah.
So it works, doesn't it? Because this was also the same base. Our exponent was 1.
No, the negative 5, why would negative exponent work inside parentheses not work? When you make you actually have a number when you get negative.
Oh, so are you talking about if this was like a negative number in here, which is what's happening on 8?
Yeah.
Yeah? So why does it not work on 8 is what your ex is asking. Because you can actually type that in your calculator. Because since it's natural log and you have a natural log key. Did you try it on your calculator? What did you get? Error. Does anybody remember why?
I know it's it's under the negative instead of like from 0 to infinity. Why would a negative exponent work in the?
Okay, so let's think about it this way here for this guy. So if this is natural log of negative 6, and let's say that equals y, right? Just to kind of match the other format. Now we know this is base e, so we can raise it to e to the y equals negative 6. Now try a couple different exponents. Will any of them give us negative 6 as an answer? Because you can try e to the 1, which is 2.71 something. E to the 2 will just increase from there, right? Because we're going with. Now, what if we did e to the 0? What will we get?
1.
Yeah, because that's the 0 exponent rule. We're going to get 1. Okay, now let's try e to the negative 1. Will we get a negative answer? So think about what happens with function e, and we looked at that graph earlier. So just as a rough sketch of this graph, something like this, right? No value of y is going to get you to negative 6 down here, right? Because where does our exponential function stop? It stops right at the x-axis. We get closer and closer to 0, but we're not going to get a negative answer. So you can't actually solve, even when we convert it into an exponential form, since we cannot get an answer, that's why a negative inside the logarithm doesn't work. But when you have a negative exponent on that e, we don't have any restrictions on exponents. It's just what's the number on the inside. Now, if this value ended up becoming negative, then it wouldn't have worked. But e to the negative 5, again, will get us closer to 0, but we won't get into negative. So does that make sense? Yeah? Alrighty, very good. So this one here is, I don't know how I want to say this. So basically just say that -6 is not in the domain of natural log of x, so that's why it doesn't work. You're looking at undefined as an answer, I guess I would say, instead of error. Are we okay on these 5 examples? Did anybody else have any other question on it? No? Okay, so the next part we're actually getting into is going to be the graphs of what these logarithmic functions will look like. So remember how we again talked about exponentials being inverses of logarithmic functions. So when it actually comes to graphing, we use that same idea again. So what we actually do is graph our exponential function and then graph its reflection as the logarithmic function. And remember, for inverse functions, we always use the line of reflection as the line y equals x, which is that oblique line with slope of +1. So we are going to start by graphing the exponential function, draw its reflection as the logarithmic function. And they are also mentioning, now we already talked about how the domain and range switch places, but the horizontal asymptote for the exponential function will replace and become the vertical asymptote. So since x-axis is the horizontal asymptote for an exponential, the y-axis will become the vertical asymptote for the logarithm function. So let's take a look at this example here. They're asking us to graph log of x with base 6. Okay, so since this is a base 6 logarithm, its exponential function is going to be the base 6 exponential function. Okay, so base 6 on the log will be the base 6 on the exponential function. The first thing we're actually going to do is create a table for the exponential function first. So remember, again, we can use our 5 points to help us out with the graphing. So if you will go ahead and calculate those ordered pairs and tell me what you come up with. So what do we get for -2?
136.
136, yeah. Which is going to be approximately 0.027 maybe for -1. 1/6, which will be approximately 0.17 maybe at 0.
1,
Okay, 1 at 1
6,
and at 2.
36.
Alrighty. So let's see what that graph will look like. 0, 1 right here, 1 and 6. 236 will be somewhere over there, and then on this side, we're just getting closer to the x-axis. So it'll kind of look something like this. Looks like my alignment's actually a little off on the screen. Let me see if I can do that one more time. Now, do you know what we need to do to graph our reflection? Where would we start?
So, because it's the inverse, doesn't like the values just kind of like switch? So the one for like -2 becomes 36, the one for -1 becomes 6.
Oh, no, not in that way. They will switch, but not in that way, because you're just interchanging you're just bringing these guys to the top and bringing them to the bottom. No.
So does it become 2 and 136 and 1 and 16? And I'm trying to figure out this which two. I don't know. It just
Nope, they don't become negative either.
Isn't it just that the x value and the y value switch places?
Yeah, because remember how our domain and range switch places? So that's basically the x will now become y and the y will become x. So it's the x and y values that are switching places. So this table, I guess, for our logarithm will become 1 over 36 here, -2 here, so 1/6, -1, 1, 0, 6, 1, and 36, 2. Whoa. Why are you doing that? 136, -2, 1/6, -1. Okay. Now the one thing I will ask you to do is additionally graph your y equals x line. So remember, those will be ordered pairs at 0, 0, 1, 1, 2, 2, 3, 3, and then it will be -1, -1 here, -2, -2, -3, -3. And since this is just our line to show us the reflection, we'll do that as a dashed or a dotted line. Okay. And then using our switched ordered pairs, we'll go ahead and graph the logarithmic function, which will now be at 1, 0, 6, 1, and then 36, 2, of course, is beyond our scope. And then here, for y value of -1, we're getting closer to 0. I'm getting closer to 0 here. Okay, so let's see. He's going to end up going this way. And you know, of course, the idea of drawing that y equals x line is so that we can kind of see how it looks like in reflection. So of course, with respect to that y equals x line, this upper part of our exponential function is the one that's being reflected here on the right-hand side. And then this arm of the exponential function is the one that's being reflected going down this way. Okay, so let's talk about the exponential function first. Remember again, domain for all exponential functions is negative to positive infinity. The range for the exponential function again starts at 0, goes up to positive infinity. Horizontal asymptote is at the x-axis or the line y equals 0. The y-intercept is at the point 0, 1. And we also know that this is an increasing function. Yes. I thought you raised your hand.
No.
No? Okay. So these were all the properties that we talked about in last section, right? When we did our exponential function. Now let's see, when we did the inverse, how did these properties transfer to our logarithmic function? So when we talk about the domain for the log function, you should again be able to verify we're starting at 0 and only going to positive infinity on the x-axis, and again, not including 0. Our range for the logarithm function, this arm, of course, is going down to negative infinity. This arm, as it goes right, will also start going up. So it's going to positive infinity. So your range is negative to positive infinity. So, of course, your domain and range have switched places from the exponent to the logarithm. We don't have a horizontal asymptote anymore, right? We have a vertical asymptote, and that's happening right here at the y-axis. So this arm of our graph gets really close to the y-axis, but it doesn't touch, it doesn't cross it. So that's going to be the line x equals 0, or the y-axis. Okay. Do we have a y-intercept? Okay, so what did that y-intercept change into for this function? Yeah, very good. It changes into an x-intercept. And of course, that is happening at 1, 0. You're basically just reversing that ordered pair and you get 1, 0 for the x-intercept. Now, is this an increasing or a decreasing function? Increasing, because as we go from left to right, our y values are getting larger. So that's an increasing function also. Okay. And we should be doing some of that comparison here. Again, our logarithmic functions are also one-to-one. So if you were drawing a horizontal line through the graph, you should see it only crosses the graph at one point. It's an increasing function. So if you compare them, the graph we just did with the graphs of our common log and natural log. So the yellow one is the natural log function and the red one is the common log here. You can kind of see it has that general shape. It's following the same properties. Domain is going from 0 to infinity, not including 0. Range is using all y values. X-intercept at 1, 0. Vertical asymptote at the y-axis. And then, of course, they are both increasing functions as well. So a lot of these properties are, of course, translating from one function to the other. And that's actually based on the base of your logarithm. Just like for exponential functions, if your base was greater than 1, your graph was increasing. Same thing happens with logarithmic functions. If that base on your logarithm is a number greater than 1, so like 6, 10, base e, all of those numbers are greater than 1, we have an increasing function. If we change the base of our logarithm to a value between 0 and 1, that's when our function starts decreasing, and that's what we're looking at here in example 10. So you can see we have a logarithm with a base of 1/6 now. So let's see how that changes our graph. So for this guy, I don't want to use red. We are graphing log with base 1/6 of x. What will be its inverse exponential function?
One-sixth to the power of
Yes,
x.
same base, 1/6 to the power of x. You can also think about it as 6 to the negative x. Either one of those are going to be our inverse function. So just like we did with the previous example, let's start with the table for our exponential function first. I will use the same 5 points. Do we have our ordered pairs for 1, 6x? For -2? Yeah, so this is actually, Amy, what you were talking about before. This is where your 36 and 136 will change places. So now we will have 36 here for -1, 6, 0, 1 for 1, 1, 6, and 136, which this guy was approximately 0.17, I think, and 0.027. Okay. So let's go ahead and do a graph for the exponential again. This will be at 0, 1, -1, 6, and then we're getting closer to 0 here. Okay, and I'm actually also going to go ahead and draw my y equals x line for the reflection. Okay, so just like we did in the previous example, just change your x and y values to create the table for the logarithmic function. Now this graph here for the logarithm is again at 1, 0, at 6, -1, 6, -1, 36, -2, with 2 here. At 1/6, we are at +1. At 1/36, we are at +2. So this function will actually, again, from the x-intercept, will go up this way. And then this arm will come down this way. And this is our log of base 1/6 of x. So quick comparison again. Domain for exponential function, range. So we're still using all x values for the domain, 0 to infinity for the range. Horizontal asymptote at y equals 0, which is our x-axis. y-intercept at 0, 1. Those properties pretty much stay same for a lot of these functions, right? Now, increasing or decreasing for the exponential? Decreasing, yeah, because it's going down. Y values are getting smaller. Now let's see how they translate it into our logarithmic function. Okay, so domain for this guy will be
No, oh.
domain for the log function.
0, 2.
Yeah, because your range and domain change places from the exponential, so it's going from 0 to infinity. Range would be the one, right? Going from negative to positive infinity. Now, horizontal asymptote? Yes, no?
No.
No, what will it be? Vertical at what value? Very good. X equals 0, which happens to be our y-axis. Again, no y-intercept. X-intercept at 1, 0. And what's happening with increasing or decreasing with the logarithmic function? It is decreasing because as we are going from left to right, our y values will continue to get smaller. So this is a decreasing function, which is what we anticipated since they told us any base between 0 and 1 will give us a decreasing function, which is what we had here. Questions on number 10? Nope. Alrighty, so that gets us to, let's quickly talk about the properties, and then we'll come back and pick up with the logarithmic family. So again, you should notice all of these properties will pretty much stay the same for all log functions. We've got, of course, when our base a is greater than 1, the function will be increasing. When the base a is between 0 and 1, function should be decreasing. All our functions will have x-intercept at 1, 0. Vertical asymptote at y-axis, x equals 0. Domain is 0 to infinity, not including 0. Range is negative to positive infinity. Of course, these functions are 1 to 1 since we know exponential functions are their inverses, and then just how to transform it from a logarithm to an exponential function. So whatever is the base on the logarithm, that same base will be in the inverse function for the exponential. Okay. All right, guys, so we will actually finish chapter 4 on Monday because we've got the remaining part of 4.2 and 4.3. 4.4, and I had mentioned this before, is only an extension of what we're doing right now, so you only have 4 examples in 4.4. So we'll finish basically all of those sections. Next week, we're only meeting on Monday since it's Thanksgiving week, right? So we will be doing Monday and Tuesday classes. Starting Wednesday onwards, there are no classes. So I'll only see you guys on Monday next week, and then we'll come back the following Monday to take the test for chapter 4. Okay? It will then take us 1 day to do chapter 5 because it's literally only 2 sections. And it will take us maybe a day to do chapter 7, and we're done. Okay? So we're really at the end of this course now. So have a wonderful weekend. I don't know how bad it's gotten out there, but be very, very careful driving home. And I will see you guys on Monday. Oh, really? Oh, boy. Be careful. Drive slowly.
I know it was all raining before I got in here. I was like, yay, ice.